The homework for this week only has 3 questions because I thought that just covered all of it, really. So we're going to start with a 25 milliliter sample that contains some lanthanum, and that's going to be treated with an excess. So that should all automatically kind of pique your curiosity. But when you get further down, it says the oxalate from the target compound that we were looking at required this amount of permanganate to reach an endpoint. And we aren't told anything more. So we don't know how much the excess oxalate was. It doesn't really matter because the reacted oxalate is going to be represented by the permanganate that was used. So we convert the volume of permanganate into liters, and this is MnO4 minus. And then we're going to use the concentration, 0.004321 moles of permanganate per liter of permanganate. And then we start using the stoichiometry. The point is we want to find out how much of this lanthanum was in the unknown solution. This is the only chemical equation we have, but we also have this chemical formula. And this chemical formula is also going to produce some stoichiometry for us. So we have this amount of permanganate. Now I need to relate moles of permanganate to moles of oxalate. So we have, in our balanced chemical equation, we have a 2 in front of the permanganate and we have a 5 in front of the oxalate. Now this is oxalic acid, and oxalic acid contains 1 oxalate and 2 hydrogen ions. It's the oxalate that we are concerned with. So now I can relate that oxalate to lanthanum. So I have 3 moles of oxalate for every 2 moles of lanthanum. How do I know that? That's right here. That's what these subscripts represent, is a molar ratio within the chemical formula. So now I have moles of lanthanum. Now I'm looking back. It says find the molarity. So I'm going to need that 25 milliliters here in a moment. So we do our calculation, and I get 8.8848 times 10 to the minus 5, and that is moles of our La3. Now I divide that by our volume, our sample volume, 0.02500 capital L liters, in order to get that molarity. And the molarity that I get is 0.003555392 capital M molar. And I need to check here 4 significant figures throughout. So I need 4 significant figures, and I would round this to 0.003554 capital M molar. If the system counts you wrong because it's only looking for 1 value, don't worry about it. I do grade all of these manually. I believe there's another 5 indicated in the answer in the system, but that's not something you need to really be concerned with. Now, the next question is a back titration. This is an indirect titration. So we have the carbon monoxide found in a sample, or there is carbon monoxide in a sample, 20.3 liters. I'm going to need that at the end. I don't need that yet. So I have this chemical reaction. I have iodine that's collected and it reacts. And then we have an excess of sodium thiosulfate. So in this case, I'm going to be using the total is equal to excess plus reacted, and these are all moles. But in this case, we're looking at moles of the thiosulfate specifically, S2O32 minus. Okay, that's what we're looking at here. So what is the total amount of thiosulfate that was added to the system? Well, that's represented by this volume multiplied by its molarity. And again, this is thiosulfate, so I'm just going to run that calculation real fast. And I get 9.08325. I'm just going to give you all of the digits in my calculator, times 10 to the minus 5th. And that is moles of thiosulfate. So the excess thiosulfate is back titrated with, let's erase this so that we don't get confused, this is represented by the back titration of 0.00216 liters of a 0.00947 moles per liter, and this is iodine. So now we need to use some stoichiometry. How do I convert those moles of iodine into moles of thiosulfate? Well, 1 mole of iodine reacts with 2 moles of S2O3 2-. And I know that because I'm given this second chemical equation down here. So here is my total. This is going to be my excess moles, so it's 0.00216 times 0.00947 times 2. I get 4.09. Again, I'm going to give you all of the digits in my calculator. 104. And that's times 10 to the negative 5th moles of thiosulfate. That is the excess. So now I can calculate how many moles of thiosulfate actually reacted. So I perform this subtraction and I get 4.99221, again, all of the digits in my calculator, times 10 to the negative 5 moles of thiosulfate reacted initially. Oh my. Yeah, okay. So now I need to use the first chemical equation or the second chemical equation, and I need to, or both, and convert these into moles of CO in the original sample. So I have my moles of thiosulfate, and for every mole, 2 moles of thiosulfate react with 1 mole of I2. And then I go up to the top equation. 1 mole of I2 is produced from 5 moles of CO. So then I can perform this equation, this calculation, and I get 1.248055. Again, all of the digits in my calculator times 10 to the negative 4. That's moles of carbon monoxide. The question asks for the concentration in milligrams per liter. So I need to convert those moles into grams. Well, at least I'm going to convert it into grams first by using the molar mass, 28.01 grams of carbon monoxide per mole of carbon monoxide. And in 1 gram, we have 1,000 milligrams. So I perform that calculation, and I get that there are 3.4957, it keeps going, but this is milligrams of CO in that sample. Well, that sample was 20.3 liters. So I divide this by 20.3, and I get 0.172 milligrams per liter. Now, I want to round that to 3 significant figures. There are 3 significant figures, both here in 2.16 as well as 8.25, 20.3, and 0.00947. So I would actually enter 0.172. That is milligrams per liter. Now, question number 3 is another back titration. This involves understanding, again, the total and the excess and where they come from. So our original sample is 1.223 grams. So that is our sample. Now, what is our total, excess, and reacted? What are we looking at? So we're looking at excess. It says right here, excess silver titrated with this. So I'm looking at the reaction of silver here. So my total silver is going to be equal to my excess silver plus reacted silver. So what represents the total silver? We have the total silver that was put into the system is represented by 0.04000 liters of silver times its molarity, 0.07891 moles per liter. And again, this is silver. So that's my total silver in the system. I'm just going to work that calculation real quick. And I get that there are 3.1564 times 10 to the negative 3rd moles of silver total. So the excess silver, what is the excess silver being represented by? Let's see. The excess silver was titrated with 11.27 milliliters of 0.1000 molar KSCN. So that's what's going to represent our excess silver. So we're going to first start with that volume. And this is KSCN. We're going to multiply it by its molarity. And then we need to find some stoichiometry, but you know what? I didn't balance those equations. So let's balance those equations real fast down here. Okay, so I've balanced these equations. If you aren't sure how to balance these equations or these don't look like something you can do, please reach out for some additional help with balancing equations. So here we're working up here, moles of KSCN. So I'm looking at this bottom equation first. 1 mole of SCN minus reacts with 1 mole of Ag plus. So that's where I want to go first. 0.01127 times 0.1 times 1 divided by 1. And this is our excess silver. So I have 1.127 times 10 to the negative 3 moles of silver in excess. And I can then calculate the moles of reacted silver by a simple subtraction problem. And I get that there are 2.0294 times 10 to the minus third moles of silver that reacted. Now we have to use some stoichiometry and some chemistry. So that reacted silver, 2.0294 times 10 to the minus third moles. We need to use our balanced chemical equations because the point is what we're looking for is this AS406. So this is our target. And we are here. So 3 moles of Ag plus, and this is from knowing that AgNO3 breaks up completely because it is a soluble compound. Breaks up completely like this. So 3 moles of the Ag plus react with 1 mole ASO43 minus. Then we can go up here because 4 moles of ASO43 minus are created when 1 mole of AS406, which is our target, reacts with water. So now we can perform this calculation and get 1.691166, it repeats, times 10 to the negative fourth. What is that? That is moles of AS406. We're looking for the percent of AS406, so I'm going to convert that into grams because my original sample was in grams using the molar mass. The molar mass is 395.68 grams per mole. So just to take it a half a step back, I'm using this 1.69116 that repeats times 10 to the negative fourth because that represents my moles of AS406, and I'm converting that into grams by multiplying it by the molar mass. And I get 0.066916, and that is grams of this stuff, this arsenic compound, in my original sample. Now to find the percent, I'm going to take 100 times the ratio of my 0.066916 grams divided by the total sample mass, 1.223 grams. And I get 5.47. I actually get 5.471. I believe the system says 5.470, something like that. I'm not going to count you wrong for. Remember, showing your work is better than not showing your work. If you have questions, please reach out.